I read a 52-page slide deck, one page at a time, all the way through. The person giving the talk is Terence Tao. The title is Mathematics in the Age of AI. You'd probably assume a talk with that title is about whether AI can actually do mathematics. But on page 8, right after he puts that question on the table, he does something I didn't see coming. He says, "I'm not going to talk about it." What he actually came to say is this: mathematics is moving out of an era of proof scarcity and into an era of proof abundance. I'm relaying this. The primary source is the slide deck he posted on his own site, 52 pages.
The deck is Tao's own, from his public lecture at the International Congress of Mathematicians, ICM 2026, on July 24, 2026. His listed affiliation is the University of California, Los Angeles. One more thing. The Chinese language retellings circulating online were not used. Every fact in this episode comes from his slides and one clip of the original audio.
Let's place the man and disclose the interests while we're at it. Tao is one of the best-known mathematicians alive. I don't need to sell you on that. What I do need to say is something else. He is not a bystander here. The last page of this talk lists new workflows and infrastructure, and one of them is an optimization constants database hosted on GitHub under the account name Teorth. That is his own account. And in a footnote, he admits that this very slide deck used AI tools to autocomplete text and generate diagrams. So he is both the one raising concerns and one of the people building and using this stuff. That doesn't make him wrong. But you deserve to know he's standing inside the field, not outside it. Now, the thing I didn't see coming. On page 8, he introduces something he calls the AI capability conjecture. Roughly. At some point in the near future, some AI tools, at some cost, with some level of human supervision, will be able to accomplish some research-level mathematical tasks in some fields, with some success rate and at some level of correctness and quality. He says himself that every one of those sums is a placeholder. How you fill them in gives you a different version of the conjecture. And then he says, this talk is not about that conjecture.
He sets up a working hypothesis instead and asks the audience to assume it holds. His words, in effect: I am not asking you to want it to be true, to believe it, or to accept it. This is a conditional analysis.
I read that line twice. Because every argument about AI right now is stuck in the same place. Can it actually do the thing? Until that's settled, nothing else gets discussed. His move is this: cut that question out entirely. Assume it can. Then ask one thing. What is it that we ourselves want? This is an avoidance. On page 12, he says exactly what he thinks of the current evidence. Most of the public evidence about AI capability was not gathered under controlled scientific conditions, is heavily subject to reporting bias and non-scientific incentives, and some costs and variables were never disclosed at all. He knows exactly what that battlefield looks like. He just doesn't think standing on it and arguing solves the thing he's actually worried about. So what is he worried about? He puts it in heavy terms. We are entering a crisis in foundations. But note this. The object of this crisis isn't logic. It's the mathematical community's own values and practices. Before he gets there, he lays down a historical coordinate, and I think it's the most elegant piece of design in the whole talk. He says, a little over a century ago, mathematics went through a crisis in foundations. For the centuries before that, mathematics ran on what he calls naive foundations. What is a set? What is a number? What is infinity? What are the axioms of mathematics? Those were largely left for the philosophers to worry about.
The turning point was Russell's paradox in 1901, and the Gödel incompleteness theorems in 1931. They forced working mathematicians to go back and examine the assumptions they had been taking for granted.
That turbulent stretch ran roughly from 1900 to 1930. His conclusion about it: the process was messy, but the end product was extremely valuable. Mathematics came out of it with an explicit, rigorous, standardized foundational framework, still in use today. And then he says, I believe we are entering a similarly turbulent period. Except this time, what gets dragged out for re-examination isn't what is a number. It's what are we doing mathematics for? Before we go further, here's a hard number. It's the one place in the whole talk where he cites a concrete result.
An independent assessment called first proof. Each batch is 10 new research-level problems. The second batch ran on May 28, 2026, under controlled scientific conditions against 4 AI harnesses, refereed by experts on both correctness and exposition. Of the 10 problems, 7 were solved at publication-level quality by at least one team. Compute cost per problem ranged from $10 to $1,000.
Drop any one of those 4 numbers, and it distorts. 7 out of 10. Controlled conditions. 4 systems. $10 to $1,000. All right, now into his actual argument. He asks a question. What exactly are the goals of the mathematical community? And he adds one clause deliberately. Not just the goals we state to the public and to funding agencies, but the ones we actually pursue in practice. He lists a string of them. Solve unsolved problems. Develop new theories and techniques. Understand the world around us. Build a community of mathematicians. Train the next generation. Contribute to a shared network of knowledge. Create works of enduring aesthetic value. The key is the next line. In the past, these goals were positively correlated. Progress on one usually brought progress on the others. So you could use one or two of them as proxies for the rest and leave the others unstated. And then he brings out Goodhart's law.
Goodhart's law, 1975. When a measure becomes a target, it ceases to be a good measure.
He adds a line after it that I found pretty pointed. Generative AI is inherently ungrounded, and combined with the financial incentives of AI companies, those two things make AI tools especially vulnerable to this law. I'm relaying that as he said it, not adding to it. His inference. Excessive AI optimization may cause those previously aligned goals to diverge from each other. What comes next is the skeleton of the whole talk, and I think the part most worth remembering. He revises one goal 4 times, and each revision is forced by a hole in the one before it. Version 1. Solve as many unsolved problems as possible. He says we didn't need AI to see the risk in that one. You end up with a pile of incorrect solutions to major open problems. Version 2. Solve as many unsolved problems as possible and verify that they're correct. He says AI and auto-formalization have genuinely accelerated both proof generation and proof verification. But then he poses a question. What if an AI generates a very long proof and nobody, including the human who typed the prompt, understands it?
He gives a real example. The site Ertis problems already contains dozens of AI-generated proof submissions. Many are probably correct, but no human expert has yet volunteered to verify and vouch for them. In several cases, even the submitters declared themselves unqualified to do so.
So he asks, could we end up with a verified major result that no human understands well enough to explain? Version 3. Solve, verify, and make sure the result can be clearly communicated and understood. This section has the most counterintuitive line in the talk, so I'll take it on its own. First, he describes where AI proofwriting stands. Spelling, grammar, formatting, near flawless. He even adds a footnote saying arguably too flawless. The problem is that it often goes on at length about trivialities while passing briefly over the most interesting and novel part, or even obscuring it. It also often fails to connect the result to existing literature. So far, understandable. The counterintuitive part is the next step. He says even exposition can be over-optimized. A proof can end up written too slickly, with the routine parts and the genuinely hard parts presented as equally easy to digest. Whereas in a human-written proof, the places the author found difficult usually leave behind some natural friction. And that friction signals the reader. Slow down. Pay attention here. Over-polishing with AI strips out both the artificial friction and the natural friction, without actually helping the reader learn the key ideas.
His words, roughly. Paradoxically, the mistakes in human exposition can end up being helpful to the reader.
He also includes one page that's just an object. a 1991 paper of Bourgain covered in annotations he made himself when he was much younger. Nothing is written on that slide. It's just the paper. I think it's the page in the whole talk that needs the least explanation. And then he quotes something from 1994.
William Thurston, on Proof and Progress in Mathematics, 1994. Roughly. We are not trying to meet some abstract production quota of definitions, theorems, and proofs. The measure of our success is whether what we do enables people to understand and think more clearly about math.
Version 4. Solve, verify, communicate clearly, and have it digested and accepted by the community. He says being correct and readable still isn't enough. Other mathematicians have to actually digest the result and absorb it into their own work. Authors can help with that by describing their own insights and the story of how they got there. But he points out, current AI tools are quite opaque about their own problem-solving process, especially proprietary models whose internals are a corporate secret. And community acceptance is, by its nature, slow and human. It cannot be optimized by the authors and their AI alone. And he doesn't stop there. He says even publication isn't necessarily the end state. Results that really matter eventually have to enter the definitive textbooks and references of the field and get taught to the next generation. He calls that canonicalization. About canonicalization, he offers 3 judgments, and I think this is where the talk lands. It is the slowest stage of all. It is the stage least amenable to optimization by AI, and it is the most valuable part of the entire process. Then he adds one more cut. The success AI has in mathematics today rests precisely on the canonical theories humans built painstakingly over centuries. All right, here's the full chain. Generation, verification, exposition, publication, digestion, canonicalization. His judgment. If that working hypothesis holds and policy and culture don't change, this chain jams everywhere.
He gives the phenomenon a name, proof indigestion. He lists the jams one by one. AI proofs waiting to be verified will pile up. Verified proofs with nobody to write a readable version will pile up. Even correct and well-written ones will swamp traditional peer review by sheer volume. And even published, there will be too many for the community to work into definitive form.
And then the line. We will move from an era of proof scarcity into an era of proof abundance. He says one more thing that I think is easy to miss. Some signs of that indigestion are already happening, and the chain was already strained before modern AI showed up. Now let's set out the chairs. I count 5 here, one at a time, and I'm not sitting in any of them. Chair 1, the people racing to solve it first. Their position. Solving open problems is the hardest currency in this profession. Whoever gets there first scores. That's not a bad motive. That's this field's incentive structure, built over centuries. Chair 2, the verifiers and the referees. Tao points this out specifically. This work is usually regarded as less prestigious than generating proofs, but it is an essential part of the profession. And it's precisely the step that converts individual achievement into collective progress. This chair is now facing dozens of times the volume. Chair 3. The people who submitted proofs, they don't understand themselves. Let me be clear. This chair is not the villain. Some of them explicitly declared themselves unqualified to verify. That's honesty, not freeloading. The tools handed them a capability they never had, and the institution that catches that capability doesn't exist yet. Chair 4. Students and the next generation. He says this specifically in the closing. In education and training, emphasizing the human part of the work and tightly restricting AI use is crucial. The people in this chair have no voice yet, but they carry the effects the longest. Chair 5, and the easiest one to miss. Everyone who makes a living off mathematics that has already been digested, including AI itself. That's not me saying it. That's him. AI's success in mathematics depends on those canonical theories. If canonicalization jams shut, the first one to go hungry might be the next generation of models. Historical coordinates. Which moment in history does this resemble? He gave us one himself. The foundational crisis a century ago. turbulent, but the product was extremely valuable. That's an ending where it got fixed. I'll give you two more. They end differently, and I'm not picking. Second, academic publishing itself. Once publish or perish caught on, paper count became the measure, and then the measure became the target. Goodhart's law already ran its full course in academia, and it still isn't fixed today. Predatory journals, salami slicing, citation rings, all still here. The answer this coordinate gives: a field may simply never fix it and carry the defect along for decades. Third, code review in the software industry. Writing code got fast first, so review became the bottleneck. The industry did eventually build new processes: automated testing, continuous integration, a review culture. The jam was cleared. But the price was this. Those processes grew into a new layer of burden, and now that AI writes the code, the same bottleneck is back again. The answer this third coordinate gives: the jam can be cleared, but the fix becomes a new cost, and it may only hold for one generation. I give you three because handing you only the foundational crisis would be comforting you. Last, my take, and what I'll be watching. My take is this: the most informative thing in this talk isn't 7 out of 10 problems solved. It's the move itself, cutting the question of whether AI can do it out of the talk entirely. Because that question has an end. Time will answer it sooner or later. And the question he exposed by cutting it will not be answered by time. What is it that we want? And the answer to that one doesn't depend on how strong the model gets. Here's the most actionable thing he offers, relayed as he gave it.
His rule of thumb. If the authors cannot convincingly demonstrate that they can give a clear, expert-level talk on the result, correct and properly attributed, then the result should not be published.
What I find clever about that is that it doesn't judge whether you used AI. It judges exactly one thing: whether you understand what you handed in. And one more he keeps coming back to: normalize the responsible disclosure of AI assistance. The worst case he wants to avoid: authors use AI covertly and hide it to dodge criticism from their peers. And the footnote on that very page reads: AI tools were used to autocomplete text and generate diagrams in these slides. In the same document, he did the thing he was arguing for. By the way, he left another footnote on a different page. All M dashes in these slides were human-generated. It's a joke, but it pairs with the disclosure footnote. One says, here's where I used it. The other says, here's where I didn't. That calibration works better than any argument. 3 signals I'll be watching. 1. The next first proof batch. He says more are planned. One batch at 7 out of 10 can be luck. A trend across several batches is evidence. And watch what happens to that cost range. 2. Whether any journal or society actually writes the authors must be able to explain it into their submission requirements. That's the line between a suggestion and a rule, and it'll be easy to spot. 3. Whether anyone picks up the digestion end. Verification, exposition, canonicalization. The prestige and the payoff are all lower than solving. If that incentive doesn't change, shouting "let's value digestion" more accomplishes nothing. Whoever puts money and status on that end first is where it loosens first. As for you and me, this talk is about mathematics, but swap a few words and the chain still holds. Generation got cheap, while verification, explaining it clearly, getting others to accept it, and finally settling into something definitive. None of those got cheaper. The work in front of you is probably jammed at the same place. That's where I'll leave this one. Next one, coming up.